All right, I'm going to talk about volumes of solids of revolution. This would be part one, where I'm going to expose you to just the theoretical parts of this one. Okay, and in part two, I'll do quite a few problems and solidify the concept. First things first. Suppose we take an area that looks like this, the rectangular area, and spin it about this line of revolution. Any idea what kind of a solid would result? Let's say this has some magical properties as it is traversing, as it's rotating about the line of revolution, it's actually generating a solid. I'm sure a lot of you would agree, all of you would agree, that it would generate a cylinder, right? And the length of this cylinder, or the height of the cylinder, this dimension, would be exactly the same as this dimension, the length of the rectangle. And the radius of the cylinder would be whatever this dimension is, the width of the rectangle, right? Keep that in mind. Now, let's change things just a little. What if there's a gap between the bottom of the rectangular area and the line of revolution? I'm sure you would agree. In that case, we would have a hollow cylinder. That means you have a nice solid cylinder into which you drilled a circular hole all the way through. What's the radius of the outer cylinder? That is the outer radius of this hollow cylinder. That would be the distance from this line of revolution to the top point of this rectangle. Okay, so that would be the radius of the outer radius of the hollow cylinder, and the inner radius, that is the radius of the hole, would be the distance from the line of revolution to the bottom part, the bottom point of the rectangle. Cool. Now, what if we were to spin a right triangle like this about this line of revolution? And I'm sure you would agree, we would get a cone, right? The radius of the cone would be this dimension. The radius of the cone, this one, would be equal to this dimension. And the slant height of the cone would be this the hypotenuse of the right triangle. Okay. Now, we're looking at some simple figures like this because eventually our objective is not to just look at areas that are nice and rectangles and triangles, but instead, what if we were to have two curves? Some y equals f of x curve and another y equals g of x curve, and we are spinning the area between those two curves about a certain line of revolution. We are slightly less interested in the shape of that resulting solid. We are more interested in the volume of that solid, and that's what we're going to find. So, in order to be able to do something like that, we need to find what happens in a situation like this. For example, we have a thin itty bitty rectangle. It's pretty long compared to its thickness, and that is there's a gap between these two, between the bottom of that rectangle and the line of revolution, and this is spun around. Well, it's kind of like that hollow cylinder, would you agree? The only difference is it's a little bit on the thinner side. Well, that would produce a washer. If you know what a washer is, anytime you try to put a bolt and a screw, then it's a good idea to put a washer in between. So anyway, that's an engineering aspect of it. More than that. So this is a washer. If you are having a hard time figuring out exactly what this washer is, imagine any coin, a circular coin, a cylindrical coin, like a quarter. You drill a hole in the center, then you got a washer. As simple as that. Okay. And that washer would have an inner radius and an outer radius. Okay. And if you actually see this washer from the side, then you would see that they are perfect circles with the inner inside a circle having a radius of r sub I. The I is supposed to be inner radius. It is supposed to be inner, and r is the radius, and r sub o is the outer radius. Okay. Now the question is, what is the volume of this washer? Well, volume of the washer is area of cross section. What do I mean by area of cross section here? You see this circle? That area minus this hollow area. That gives you what is called the annulus, the area of the annulus or the ring area. So that is the area of cross section here times the thickness, that thickness of the washer, which is the same as this thickness that you see, the T value. Okay, and so the area of the annulus itself, the cross-sectional area, is pi times RO square minus RI square times T. So pi times the quantity RO square minus RI square times T. That's all there is to it. So this is how you find the volume of the washer. But here, I want you to take a good look at this figure. Remember this figure and remember the formula for the volume of the washer and also exactly what this R sub I and R sub O are and what T is. Okay, let me repeat that part. R sub I is the distance from the line of revolution to the closest point on the rectangle, whereas R sub O is the distance from the line of revolution to the farthest point on the rectangle. On purpose, I'm not stating this as R sub I is the distance from the line of revolution to the bottom of the rectangle. Well, what if the situation is that the line of revolution is up above this rectangle? In that case, R sub I would be the distance from that line of revolution to the top point of the rectangle. And R sub O would be all the way to the bottom from that line of revolution to the bottom in that case. So that's why I'm being clear about the R sub I is the distance from the line of revolution to the bottom of the rectangle, R sub O from the bottom, from the line of revolution to the top of the rectangle. Keep that in mind. And like I said, the volume of the washer itself, the formula is pi times RO square minus RI square times T. And there's another scenario. What if the rectangle's orientation is like this? It's got a length of L and a thickness of T, and this is spun about this line of revolution. In some ways, it's more or less similar to the previous case, the hollow cylinder case. But here, the idea is, even though I have given this thickness a decent dimension, it should be construed as being fairly thin compared to the radius. Well, what kind of a solid would that produce? It would produce something like a soup can, okay, or a Coke can. The thickness of the Coke can is small, but the radius is significantly large compared to the thickness. So that's the kind of solid you would get, and mathematicians and engineers would call such a thing as a shell. Okay. Now, our question is, what is the volume of this shell? And there are a couple of ways to finding the volume, but here's one way. And that is, imagine we take a pair of scissors or snips and cut this all the way up at the top. From here to here, you just cut it and open it up so that that would look like a big rectangle like this, a rectangular solid, with the thickness here being the thickness there, and this length being this length. And here is the key, the other dimension. This would be the circumference of that circle. And the circumference of this circle is 2 pi times the radius, 2 pi r. And that's what you're seeing. So when you snip this and and flatten it out and make it into a rectangle, it looks like this. Now, the volume of this shell is nothing but the volume of this rectangular solid that you see here. Well, the volume of this is fairly straightforward. 2 pi r times L gives you the cross-sectional area multiplied by the thickness. You got the volume of the washer. All right. So the key things to remember is in a situation like this, when you have a shell, R represents the distance from the line of revolution to the rectangle. The distance from the line of revolution to the rectangle. Now, obviously, some of you immediately have a question in your head, right? That is, hey, what do you mean by distance to the rectangle? Which part of the rectangle? The thing is, R value compared to the thickness is much larger. So it really doesn't make a whole lot of a difference whether you're measuring it to the bottom edge of the rectangle or the top edge of the rectangle or the middle of the rectangle. So it doesn't matter where you measure it to. I happen to show it as something from the line of revolution to the bottom of the rectangle, but it doesn't have to be. Any part of thickness of the rectangle, if you were to measure the radius to, is perfectly fine. Okay. All right, that's the first thing. That's one of the things you must remember. And also, this volume of the shell is given by 2 pi r LT. That's all you need to know.